We now go back to finding the splitting elements in the IO model. So remember that we want to find M over B splitting elements that roughly split the input into equal size lists. The first observation is that this algorithm that we covered previously actually runs in N over B IOs. The first observation is that the first part can be done in N over B IOs because we just don't need to do anything. If this is the input elements, this is already split into blocks of size B. So therefore, when I look at every block, I can think of it as being composed of B over 5 groups of size 5. Okay? So therefore, if I just read the first block, I will create, I will kind of group them into groups of size 5 elements, and then I could find the median of those 5 elements in the internal memory, essentially for free, and so on. So the first part of the algorithm, so this is O of N over B. Similarly, this is just a recursion, and the distribution is also just a normal distribution to 2 lists using one pivot or one computed median, which again can be done in N over B IOs. And then once you look at the recursion, you get N over B from steps 1 and 3, N over 5 from step 2, and 7/10 of N from step 4. Similar to the analysis of the median finding algorithm in the internal memory, which solves to N over B IOs. But the thing is, this only finds one median. If I want to do this, if I want to use this for my original problem, my IO complexity will be this much, right? Because I want to find M over B medians. This is the number of medians that I defined. And if I spend O of N over B time for every median or for every splitting element, this is going to be N times M divided by B squared, which is already way too much, so I can't do that. So we want to do something smarter. What we want to do instead is to, instead of computing M over B splitting elements, I want to compute square root M over B splitting elements, and they're not going to be perfectly splitting. Okay. What would mean perfectly splitting? What is perfect splitting is that, let me just call this X. If I have X splitting elements, a perfect splitting would be that after you split these elements into into lists, right? So you have X elements here. The size of each list should be N over X. Okay, so that would mean that is perfect splitting. Okay. What I'm looking for here is an almost perfect splitting. What I mean is that the size of each one of these lists is at most 1.5 or like 50% larger. So this is not N over X, but it's at most 3/2 of N over X. So I compute slightly fewer elements, and they're not perfectly splitting. But both of these changes only affect the constant factors in my algorithm. This is because if I analyze the quicksort algorithm, or the multivariate quicksort algorithm from the previous slide, what I get is that instead of having the base of the log being M over B, it's a square root M over B. But if you know your log rules, this square root M over B in the base of the log just goes out as a factor 2 in the constant factor, so it can be absorbed into the own notation. So therefore, this doesn't really change anything in the algorithm. All right, so how do I find these splitting elements? So remember that I want to find square root M over B splitting elements, right? So essentially, let me just call them pivots. Okay, that's a bit easier to say. I want to find the square root M over B pivots. The first thing we do is to sample this many elements. What this sampling means is that to run these 2 steps. The first step is to create N over M list of size M. So you pick one list of size M, another list of size M, etc. The number of these lists is, of course, N over M. We sort each list inside internal memory. We can do that for free because we can just fill the memory and we just sort it inside memory. That doesn't cost us any extra IOs. Once this is sorted, we pick this many elements evenly from the sorted list. Right, so we pick this to assume that these elements are sorted. we pick elements at these positions, and from every list I pick that many elements. So how many elements I pick in total? Well, I have n over m lists times a quarter of square root m over b. That is the wrong. I pick one every this many, so that means that the gap between these each elements that I pick is a quarter of square root m over b. Okay, so I pick elements such that they split each group of size m into chunks of size a quarter of square root m over b. So how many I pick? Well, I pick m divided by that number, right? So m divided by a quarter of square root m over b. And if you simplify the quarter, the 4 goes up, m cancels with m, and I left with this. So in total, I will be selecting exactly 4 times n divided by square root m over b elements. Okay. Then in the step 2, let me erase some stuff. Okay. Then in the step 2, we use a selection algorithm only over the sampled elements. Okay, so I look at the sampled elements. So let's say this is my sampled elements. How many they are? They are 4n divided by square root m over b. So these are the sampled elements. And I run the median finding algorithm from before this many times to find every that many element. In other words, we sample some elements from this evenly such that the gap between every 2 elements is 4n divided by m over b. Okay. How many we sample? Well, we sampled this divided by this. We're going to look at the math later. And that essentially is the algorithm. Let's look at the runtime analysis first. Step 1 obviously can be done in n over b IOs. This we already covered. Let's look at the step 2. In step 2, I will need to use the median finding algorithm this many times for every block, ignoring the constant factors. And running time is going to be this much because it's the size of divided by b. Okay? Because that's the number of elements I have, right? Every pivot can be find the number of elements divided by b IOs, and I need to repeat this m over b times. And once you do the math, this cancels with this, and I get n over b, right? So this whole thing magically runs in n over b IOs, and in particular, these numbers are chosen in such a way that the math works out to be n over b. So there is nothing too exciting here. And that's actually the reason why these numbers are a little bit strange, okay, such that they're cooked up to give us n over b IOs. But the more interesting thing is that why does it work? Okay, so now let's see why it works. So this is a pictorial example of how this algorithm works. So this is the step 1. The black elements are the sampled elements. So I have this memory size lists, and I have sampled this many elements from each memory. So remember that the gap, this gap between the black elements is roughly a quarter of a square root m over b. Okay. So that's because that's how we have selected these black elements. The black elements are the sampled elements. Okay. So that's the first step. I select these black elements, and there are m elements at every row. Then once I selected the black elements, I split the black elements into, or I find pivots from this black elements in such a way that the gap between every pivot is basically this much. Okay. Let's represent, yes, exactly, that's what I said. Let's represent these by these red elements. So these red elements are the split elements that I found from the black elements. What do I know about these red elements? The thing that I know about these red elements is that between every two red elements there are roughly 4n divided by m over b sampled elements. So this many black elements between them. Okay. How many normal elements would be between them? Well, between every two black elements there is at most, or there are exactly this many elements, and if you have, and you could have a little bit more left over from the right or from the left. So therefore, if you count maximum number of, let's say, normal white and black elements that can be between them, is essentially you multiply the number of black elements times by the distance or the number of white elements between the black elements. So it's going to be this times this, and if you do the math, if you simplify it, essentially ends up being this number. So therefore, between every red element, there are exactly, or there are at most, this many white elements. And this is basically as we claim. So that concludes the split finding algorithm. So we covered two sorting solutions, one distribution based and one merge based, and then I will upload some other videos later on that show that both of these algorithms are essentially optimal.